p-value. How do you find p-value? It's the extreme value and the even more extreme value compared to the observed value. Assuming you use the original mu, okay, assuming you use the original mu, and then the more extreme value than that, that's the p-value. So if that's the p-value, we will say, I want a smaller p-value to say I can reject H0. Well, if the p-value is large, I cannot reject 0. So what basically, the simple idea is, I see on that distribution, the value I observed, and then even larger than that, got a lower chance to get. Then I say, okay, if it's that lower, very low chance to get that, and we still get it, and we can suspect there's something wrong with my original assumption, the mu. And then we can say, oh, we may need to change it a little bit. Like, that's the assumption. So, the p hat, we have the p. The p value have like couple levels. Well, 5% level, 1% level, and 0.1% level. And then we use that to whether reject 0 or not reject. But the statistical significance will given to you in the question, like say 5% significant or 1% significant. Normally it's 5% or 1%. And okay, the distribution again. So how do we calculate the distribution for x bar? X bar is just like the normal mu, and then the standard deviation is the normal standard deviation divided by the square root of the number. That's the x bar distribution, and you know x bar distribution is always follow that. Okay, x bar distribution is always that. So yesterday we only talked about the one-tail one. Okay, no, last lesson we talked about one-tail one. So H0 is your mu. What is original mu? And H1 is either mu greater than that or mu less than that. Okay, it's always greater or less than. But what we have talked about in the exercise B is called a one-tail versus two-tail test. So when do we use a two-tail test, and what does the alternative hypothesis looks like? Okay, this is a two-tail test. So one-tail test is like when I say, oh, I suspect the true mean is larger than the original value, or the mean is less than the original value. That's one tail. It's absolutely larger, absolutely smaller. And what we think about the two-tail one, let's say we have H0, say that's mu equals to 10. Okay. But I start my suspect say, well, mu is not equals to 10. That will be a two-tail case, because I don't know whether it is like larger or smaller. I just think, oh, I don't think it's 10. From my observed value, I think it's not necessary to be 10. It can be something else. But I don't exactly know what is it. So this is called a two-tail test. So what's the p-value for the two-tail test? Then the mu can be larger or can be smaller. I can't tell. Okay, I can't tell. Therefore, when we look at the x-bar distribution, what we'll look at is like, for example, that's my observed value. Lowercase x-bar, that's my observed value. And then let's say if it's on the right-hand side, I will calculate whatever on the right. But you always also need to suspect on the left. So it can be less than as well. I don't know whether it's a greater or smaller one. If I just say it's not equals to, then I can suspect both sides is a less or a greater. Well, it's not really used a lot in year 12 because this is not really what that should be used. There will be other distributions need two-tail, like in uni. There's a lot of tests which need two-tail tests, but like not talking about that case in year 12. So it's not a really good use in year 12. So if you just say, well, you just need to look at your hypothesis test. If you H1, alternative hypothesis, if H1 is not equals to, you must think about two sides. So that's the observed value on the right, and then exactly symmetrical area on the left. So in this case, the p-value is 2 probability x bar greater than x bar because it's symmetrical area. I need to think about the opposite one as well. So the p-value is twice as large as before. Okay, so twice as large as before. So it's actually, we can easily reject, well, not easily, relatively easily to reject the hypothesis when it's only one tail. Because if you talk about two tail, it will be twice as large as that. Then the p-value increased. You don't want that large p-value. I want a smaller p-value. So two-tailed test will be harder to reject compared to the one-tailed test. If they have exactly same situation, same mean, same standard deviation, same observed value, two-tailed test will be hard to reject compared to the one-tailed one. Okay, so when the alternative hypothesis is directional, say less than or greater than, we carry out one-tailed test. When this is not directional, say it's just with a not equal sign, then we say that's a two-tailed test. All right, and we have the p-value of two-tailed test is twice as the p-value of the one-tailed test. That's what I explained on the diagram. All right, have a look at example 4. Say example 4 says a machine is designed to produce rope with breaking strain of 1,000 Newton and standard deviation of 21 Newton. To test whether the machine is still operating as it should, a random sample of 30 pieces, okay, 30 pieces n equals to 30 of the rope was selected and found to have a mean of that. So you observed x bar is 1012. Okay, that's your observed value. Okay, so let's say that is original x is normally distributed with 1,021 Newton. Then your x bar needs to be normally distributed with 1,021 over square root of 30 squared. That's the new standard deviation for x bar. If you have the distribution for x, you definitely have the distribution for x bar as well. Well, even though x is not normally distributed, remember the central limit theorem, I still have like x bar as a normal distribution. So x bar is always normally distributed when n is large enough. Then what I want to think about is there evidence at 5% significance level that breaking strain has increased? Okay, the word increase is directional. So A, I would say hypothesis 0 like is mu equals to 1,000. I still assume that's 1,000. But H1, I would say mu is greater than 1,000. Because I observed 1012, I would say, well, it's larger than what should be. And can I just assume that it's larger? Okay. So 5% significance level to whether we can reject it. If it's directional, I will talk about probability x bar is greater than 1012, the value observed. Like what you observed, is that like enough evidence to talk about that? So you talk about the value greater than that. So we have menu 5521012, and we have to infinity. Okay, and mu is 1,000. Well, you still use the original mu, like whatever you have. And then standard deviation is 21 divided by square root of 30. Okay, you are talking about the x bar distribution, not the x distribution. So you must take the n into consideration, like what is the standard deviation now for x bar. Okay, and then press enter. What do you have? 0.00087. That's the p-value. When you talk about whether I can reject or not reject, I must talk about the p-value. So p-value is the like greater than that, and that's 0.00087. Do you think you can reject it? Can you reject H0? I didn't say accept H1, like I can't accept H1. I can only reject or not reject. So should I reject H0 in this case? Why not? Okay, 5 significance level. Is the p-value greater than that 5% I reject, or less than that 5% I reject? Less than 5%. Because what the purpose is, you want to show the value you get is not that easy to get. Then I will go back to suspect, okay, there must be something wrong. For example, this question I said, the value equal or greater than 1012 is only 0.087% to get. It's a very, very low chance to get it. Then I said, well, it's not because of the sample variance, like it's just like not coincidence. Like I get a really hard value. Like I'm really hard to get value from what I assumed. I assumed mu is 1000, but like from what I assumed, it's very hard to get the value I observed, which means like it's not coincidence. It's not because of like just a variation between the samples. So it must be something different like I should have like for the mu value. So therefore, I need to reject H0. Does that make sense? Yes? Yes? The p-value needs to be small, okay? The smaller the p-value, the better, like the more strong evidence I can reject the H0. Okay? Okay, B. That's what we learned last lesson. For B. Is there evidence at 5 significance level show that has changed? Has changed doesn't mean change larger or change it to smaller. Let's just change. It's not that. It's just not that. So H0 is still mu equals to 1000. H1 must be mu not equals to 1000. So it can be anything else. It's just not 1000. Okay. And okay, then the p-value will be twice as before. Okay, remember the two-tailed thing? Like before, what I have is, like what I assume the distribution is like that. Okay, I assume the distribution is like that. It's 1000 here with standard deviation is 21 over root 30. And then I observe a value 1012 and I said that area is 0.087%. Then if it's two-tailed test, I must have exactly this side as well, because I cannot only consider about the greater case, I also need to consider about the less case. So it's two lots of that. That's 0.0017. Should I reject the hypothesis 0 or not? Reject or not? What percentage is that? Less than 5%. So reject is H0. Like it's strong. It's enough evidence to reject H0. Like what you observed is enough evidence to reject H0.
It's so hard to get. It's so hard to get above 1.13.
Yep.
And that it's so hard to get above it, so you can't say the mu is sometimes.
Yeah, you can't say mu. Like what I assume from my assumed distribution. Like I think it's 1000 now, and then the distribution will be 1000 and standard deviation is 21 over root 30. Okay, that's my X bar distribution. That's what I assume my distribution will look like. And now it says like, well, I get a mu of 1012. And if I get that value or get that value above, it's only 0.087%. It's about 0.09%. It's so hard to get. Well, it's not. I'm not that confident to say it's just because the distribution looks like that, and that all the sample you get is just the one with like greater mu. But like it's maybe something wrong with my. Well, I just pick 30 things, and how bad luck am I? Like I will get a mu that hard to get. Like, well, it's possible. Well, again, it's possible. When we learn the type 1, type 2 error, it's possible. I'll tell you that's possible to get. But like, yes, it's possible, but with a really low chance to get. Well, then I need to start to suspect, well, my mu is not actually that one. Is that like clear? Like I'm doing something. Yes, I know. Like I buy something. It's really hard to get under that. And then that's from my assumption. That's all coming from my original assumption that mu is 1000. But like, you get something which is really hard to get. Well, yes, two sides. You can really just a bad luck, like you just get that. Like all the extreme ones, you get it. you get that chance, you get a 0.00087 of the chance get it. Yes, you can get it. But on the other hand side, is that hard to get? Is that because I just get that bad luck, or just because my mu is not that? My mu might be different.
No.
It's like greater. It's greater. Like my mu is actually like supposed mu is lower, but like actual mu maybe is larger. Maybe it's larger. Yeah. That's on the other hand. So like I think it's too hard to get, and I shouldn't take it. I shouldn't take that one. That's why I reject it. Okay. Well, it's still possible. Like you may get a wrong rejection. You may reject it wrongly, because you still get a 0.0087 of the chance to get this with this distribution. But you just say, oh, it's too little chance. Like I may not just get that. It must be something wrong with my mu assumption of mu. So I reject it. Yes? Okay. Have a look at the next question and have a try of that one. Just give you some time to try this. So for this question, what you have is x is normally distributed with 0.725 and 0.01. That's what we assumed. Therefore, we'll assume our x bar is 0.725 and 0.01 over square root n is 15. Go square root that. Then is a two-tailed test. So H0 is mu equals to 0.725. That's what we assumed. But H1 is mu actually equals to not equals to 0.725. What I want is a p-value. My p-value must be a two-tailed test. It's two lots of the extreme value I observed, left or right. So I observed the value of x bar, lowercase x bar, 0.721. So I observed that, which is below my mu. So I will talk about this x bar less than that value. I can't go greater. If it's greater, it's over 50% already. So it's less than that. So I will have, okay, the directional sign you have here, you shouldn't include your actual mu inside. Okay, you shouldn't include your actual mu inside. I must argue x bar is less than that. So less than 0.721, you're not including 0.725 in. If you say greater than that, what's the point? You include your mu again into the calculation. Like it's not a valid evidence. So what you have is this one. You put that into the test menu 552. So it's minus infinity to 0.721 with 0.725 over 0.01 divided by square root 15. Wait, is that 0.001? 0. Can I select? That's the one tail. Because it's a two-tailed test, I should have that. So it's 0.0047. And should I reject it or not? Reject. Okay, reject H0. It's lower than 5%. Okay, that's A. And for B, in a later test, like decide a more stringent test. Well, I don't want that easy pass. Okay, if now takes 100 bottle and the mean is 0.722 now. It's a little bit higher, but like it's still below the actual. Is there evidence to say mu is not 0.72? So again, your x bar become, but that's 0.01 divided by square root 100. So it's 0.001 now. X is normally distributed, and my H0 is still mu equals 0.725, and then my H1 is still say that mu is not equals to 0.725. And then what I will talk about is a 95, not 95, it's 1%, okay, 1%. So I'll look at the p-value. The p-value. It should be 2 loss of the extreme observed value. So x bar needs to be less than 0.722. So let's just change that to a 2 and change that to 100 instead. And I need to times this value by 2. Is 0.0027. 0.0027. Should I reject H0 in this case? Why? So what's that? Really? Take that to percentage. Yeah, how many percent? Reject. Okay, that's 0.27%. So reject. It's less than 1%. Okay, I'll say because it's less than 1%, that's less than 5%. Okay, I reject it. So this one is because it's less than 5%, I should reject it, 5%, and that's this the same, less than 5%. I'll reject it. We'll have a talk about it because it's less than what, and then we reject it.
What difference of that put lower bound to 0?
Why you put lower bounds to 0? Well, like if you think when we talk about binomial distribution, we not think about the real meaning of this variable. So let's say when we talk about the height of different people, we say it's normally distributed. Well, height cannot be below 0. And then also it can't be above like about 2.5 meters or say 2 meters. But like we still can take all these possible values. First reason is if you restrict that to 0 to 2, then the whole area under the curve is not 1 anymore. Second, the value, like because you have your mu, you have your standard deviation. You know, like within 3 standard deviations, it's already 99.7 of the values. So what has been left for those two tails is only 0.003. Like that's what has been left for the two tails. So doesn't matter. You put like 0 to the left and 2 to the right. That maybe in total just give you maybe less than 0.1% of the probability. So it's almost impossible. Like it's almost like impossible. So you don't think about that much in normal distribution. Normal distribution will take everything. You're not restricted by yourself. Because as soon as you reject it, which means your endpoint is at 0, then the whole distribution can't have an area of 1 under the curve. And that's wrong. Okay, and that's wrong. And also it won't change too much, even though you restrict at 0. Like it will be after maybe 5 decimals and start different, or 3 decimals is different. It's not going to change that much. Okay. Okay, and next thing we talk about is like, that's a two-tailed test, right? In two-tailed test, there's another way we can do things. Okay, in two-tailed test only, okay? One-tailed test, we're not going to do that. Only in two-tailed test, what we will do is, do you remember, what is it? Confidence interval. Confidence interval, about like what we talked about before for X bar. Okay, for X bar. What's the confidence interval? It's written here. That's 95% confidence interval. Okay, that's 95% confidence interval. So as I said, like it's about 95% sure that my true X bar, true mu will be included in that range, right? Okay, if we reject things at 5% significant level, which is same as we accept things in 95%, right? Yes, like if it's two-tailed is 5%. I'll say I want this middle is 95%. That's the same as we use the observed value to find the 95 confidence interval. Okay, if we find the confidence interval that's 95%, then if that range contains the mu, the H0, the mu I have in H0, which means like I don't need to reject H0 because this makes sense. While we reject at 5%, we accept it in 95%. Then we use my X bar to calculate what is called the confidence interval. If the true confidence interval will include my actual mu, which means I should accept it, right? We do not reject it. That makes sense. Not accept at all. We do not reject it. Okay, we do not reject it. So that's another way, alternative way we can calculate it as like whether we should reject H0 or not. But only works for two tails, the confidence interval method. So this is a 95 confidence interval. This is the K value, which is probability minus K Z to K. That gives you 95%. That gives you 95%. So I can work out like, for example, 1%. 1%, we reject it at 1%. Then I will have 99%. Accepted, right? 1%, 99 accepted. So this K will change as well, change it to 99%. I think it's a 2.56 at 99%. So I'll change that to 2.56 of that 1.96. Okay? So let's calculate. Example 6 says use the confidence interval method to do example 5a again. In 5a, we observe our X bar equals to 0.721 and N is a 50. So the confidence interval is X bar, well, 95% because 5 significant level to reject. So it's 1.96. Standard deviation is 0.01. Divide by square root of 50. Well, X bar is 0.721. Okay, what that equals to? 0.721 minus 1.96 times 0.01 over square root of 50. That's 0.718. Let's go 3 decimals. 0.718. And then the right-hand side boundary will be the plus. And that's approximately go up and go to change the minus into plus. And that's 0.724. Okay, 0.724. So for the observed X bar, my 95% confidence interval is 0.718 to 0.724. Okay, this do not include 0.725, which is the H0. Okay, so reject H0 at 5% significant. Significant. Significance level. So if it's 95%, does not include that. Okay, 95% does not include that. So which means it's the 5%. It's the 5% error. So I shouldn't keep H0. I should reject it. Which is the same result as before. We should reject it. Any questions about that? No? Okay. No. Let's have a look at next exercise. Okay, this one is a little bit tricky. Okay, a little bit tricky. So suppose that, well, it's nothing to do with X bar yet. Okay, I just start with a really easy question. Okay, start with a really easy question. Suppose that X is normal distribution. With mu 10 and standard deviation 5. A really normal question, okay? Do not think that much. Find the probability that a single value of X is at least 2 units from the mean. How you can represent, like, is probability of what greater or equals to 2? What I'm trying to find. I want to try and find probably what greater or equals to 2. Like, from the distance of X from the mu is at least 2 units. Let's see. Standard deviation? Well, I'm not talking about standard deviation. Say my mean is at 10. Okay? What I should have, like, is 2 units different from 2 units from that. But that's 10. Which number is two units different from that? 8 and 12, okay? 8 and 12. What I need is greater than 12, or greater or equals to 12, or less than or equals to 8. Yes? That's exactly 2 units from the 10. So what I'm looking for is X minus 10 absolute value is greater or equals to 2. Does that make sense? It's the actual distance from that X and the 10 is greater or equals to 2. So, as we said, that's 10, that's 8, that's 12. It's a normal distribution like that. Well, I'm looking for this value and this value. So that can be equals to probability that X greater or equals to 12. That also can be 2 of the probability X less than or equals to 8. 2 lots of that is symmetrical area. Okay, it's symmetrical area. It's all 2 units from the 10. And then what we do on the case. So lower bound, let's say just go negative infinity to 8. Well, mu is 10, standard deviation is 5. And then this value needs to be times by 2. That's 0.8689. Okay, so the idea of this exercise is we talk about something on 2 sides of the mu. Okay, I say the distance from the mu is what? Then it must consider about 2 sides. And it's a symmetrical area. Okay, and it's a symmetrical area. So have a look at example 8. Wait, we have another thing here. Okay, you know if I'm talking about X bar minus mu is greater than something. Okay, X minus mu is greater than something. Then if I divide both sides by sigma over square root n, divide by sigma over square root n, then I will have Z absolute on the left hand side. Does that make sense? Because it's X bar minus mu divided by standard deviation equals to Z. That's what we're looking for. Okay, X minus mu divided by standard deviation. Yes?
What does the mean
Is the distance. Well, it can be distance from the right or it can be the distance on the left. So for example, I will say z is greater or equals to 2. What I'm talking about is 2 and negative 2. It's both sides of that. It's larger than 2. The distance is larger than 2. Okay. So let's have a look at example. When you do the example, it will be much clearer. Okay. To plan its work schedule, a manufacturing company used the knowledge that the time taken to assemble a certain component is normally distributed with a mean of 15 minutes and standard deviation of 5 minutes. Let's say that's x. Normally distributed with 15 and standard deviation of 5. If actual mean assembly time is for 20 random select components is recorded, and the probability that this will differ by at least 2 minutes from the expected. Okay, what is the probability that this will be differ by at least 2 minutes from the acceptable mean of 15 minutes? Okay, so what I'm looking for is, like, let's say we have x bar. Just go step by step. We have normal distribution with 15, right? Still 15. Standard deviation is 5 divided by square root of how many? 20. So square root of that. So it's normal distribution with that. Okay, so what I'm looking for is, I want to observe something that is at least of 2 minutes differ from the actual mean. So let's sketch the x bar. That's 15, right? At least 2 minutes differ. So 2 minutes differ, so it's 30 here, right? And 17 here. At least 2 minutes differ is just those two values. I'm looking for that area actually on x bar. I will say the way I can write it is probability that x bar minus the 15 absolute is at least 2 minutes. That's the way I do it. Yes? Okay, so what I want to do is, okay, x minus mu. I already have x bar minus mu. How about I do probability? I divide that on standard deviation. So it's 2 divided by 5 over root 20. That will be the z absolute greater than that. 4, 5, and that's 2 loss of the probability that z is greater or equals to 4 root 5 of 5. Okay, z absolute is greater than something. So it can be on that side or can be on that side. So it's 2 loss of that. Well, or can be negative of that, like can be 2 loss of the negative side of it. So it is negative 4 root 5 over 5 and 0 to 1 because it's a z. And then this number needs to be times by 2. So that's 0.07374. Let's just go 0.074. Okay, let's calculate by another method. Let's change the node distribution to z. Let's have a think. Is that possible? We can calculate from this. It's from 17. Okay, it's from 17. So I will say, or less than 13, or less than 13. Let's go manual 552 minus infinity to 13, and the mu gives us 15, and the standard deviation is 5. No, not 5, not 5. The standard deviation is not 5. The standard deviation is 5 over square root 20. Yep, that's the same value as this one gives me, n times by 2. It's still the same. I can either directly from the graph to look what is it and calculate the area, or I can use, say, like this to calculate it. Okay? Okay, B. B says, if a difference of at least 2 minutes was observed, would this cause you to question whether the mean assembly time was actually 15 minutes or not? Explain your answer in terms of the appropriate hypothesis test. Use 0.5. Yep. Okay, I'm taking this 2. That's 2 is the minus sign. What I'm doing is, that's the Z, right? Greater or equal to, I'm looking for this value or this value. That's 4 root 5 over 5. That's negative 4 root 5 over 5. I can go greater than that plus less than that. But I'll just go 2 lots of the greater side or 2 lots of the smaller side. I'm just not thinking about like both sides. It's symmetrical area. Okay, B. How do you think? Do you think you will reject it? Okay, then how you calculate the hypothesis? So you say H0 mu is 15. H1 mu is not 15. It's actually a two-tailed test. What you calculate is, well, you observe something is at least 2 minutes different. So it's the probability x bar minus the mu is greater or equals to 2. That's what you observe. There are 2 minutes different and beyond. And what you get is a two-tailed test. So that probability is 0.074. That is greater than 5%. So do not reject. Okay, because at least 2% gives you something like it's really large. Okay, C. What size difference between a sample mean distribution from a sample of size 20, the hypothesis population mean, would you lead you to reject the hypothesis test? Well, like whether it's 15 minutes or not. So 2 minutes is not enough. Okay, you understand? Like 2 minutes is not enough. What you're looking at will be some. Well, it's different by even greater value, right? Like 2 is not enough, but 1 is even not enough. Like I must have a greater difference compared to my actual mean, right? And then I say it's less than 5%. So basically, I'm looking for 2 values. Okay, I need those 2 to have 5%, just 5%, right? It needs to less than 5%. I can observe something larger than that. Then it's enough, right? So what I'm looking for is what I'm looking for is the probability of x bar minus 15 is greater or equal to a particular value A. That gives me just 5%. Yes? So again, I can say that's probability that is a Z greater or equals to A divided by the standard deviation. That's the standard deviation. That equals to 5%. Sorry, what is it? What's your question? Yeah, 5% I rejected. If it's just 5, well, I'm using the, the boundary levels, like like the limit. Now you can't say 4.9. Like I'm talking about A. A is an inequality value. I'll say like when A is greater than that, at least that. Like you can't use 4.9 to calculate. It's just like we use the 5% to calculate, and then we talk about it later. You won't meet some case just give you 5%. That's like too mean. Like it will be either above. Well, it's not that easy to find a value that's just 5%. Plus, that's a continuous random variable. Okay, so it's not that easy to have 5%. So what I need to do is two laws of probability z greater than that's 2a root 5. I think. That equals to 0.05, like 5%. So again, what I'm looking for is one side only can be 0.025. 0.025. So z greater than something give you 0.025. What you need to put into the calculator is z less than that. Gives you 0.975. Okay, you can't put greater in. You can only put less than. So menu 553. So area is 0.75. 0 and 1, that's a z. You have 1.96, that's 95%. Right, that's 95. The z is 1.96 to 1.96. And then menu 3, 1. That value equals to 2 times a divided by square root 5. You're solving for comma a. A is 2.1913. Okay, a is 2.1913. So it will be at least 2.2 minutes different to reject it. Right, at least 2.2 minutes different, I can reject it. Well, with at least 2 minutes is 7.4% of the significant level. It's not good. So 2.2 minutes will be less than 5% significant level. Then I can reject it. Calculator page. Alright. Okay, the last exercise. Okay, this is very interesting. On the book, okay, the Cambridge book, no example was given. No calculation example was given. It's just like the wording example, like what is type 1 error, what is type 2 error. It's only the wording questions given. And then we find that like, oh, there's no calculations. And then we go to the paper, oh, you required calculations. So it's not like written in the book. So I find some exercise here. You need to do calculations, okay? Remember, you need to do calculations. So, very confusing thing, first of all. Errors in hypothesis testing. When you reject or do not reject something, you always have errors, okay? You always have like a probability that you reject it wrong or you do not reject it is wrong, okay? Well, whether you not reject it or reject, you always have a level of like, well, you're never sure about it. Like you don't know what it actually is. So you always have a probability that you get things wrong. But like you reject it, you have a type 1 or type 2 error. You not reject it, you have a type 1 or type 2 error. So the type 1 and type 2 error is describing the two errors we have. So the type 1 error occurs when we actually reject it. When H0 is true, we reject it. Which means what I assumed before is correct, but we reject it. That's called the type 1 error. Okay? Type 2 error is we do not reject that, but it's actually wrong. It is actually wrong. Okay, we do not reject it, but it is actually wrong. Does that make sense? Okay, so type 1 error is like one I shouldn't reject and then I reject it. But second one is what I should reject. I haven't rejected it. That's type 2 error. Okay? Okay, good. Let's have a look at that. It's very easy. Okay, it's a definition. That's what all the books have. Okay, that's it. But let's have a look at the calculations. What the calculation is talking about is the random variable x is normally distributed with mean mu. The mu doesn't know. And the variance of 12.8. And random sample of 20 observed. Let's label everything there. 20 chosen. Okay. And the value calculated from these data used to test the following non-hypothesis testing is H0 is 5, mu equals to 5, and H1 is mu greater than 5. It's a one-tailed test. Okay, so one-tailed test. Find A such that probability x greater than A, mu equals to 0.05. Do you understand what the notation is? Do you understand the notation? Okay, what's the bar? Do you know what's the bar like in probability? Given. So tell you that give you actual information that your mu is actually 5. Okay, give you actual information that tells you mu is 5, which means that H0 is correct, right? H0 is correct. Right, yes. So I want to find on this distribution, x bar distribution. So what is x bar distribution? X bar is normally distributed with 5. It is with 5. And we have standard deviation. Okay, that's a variance. So your standard deviation is this. Right? It's standard deviation divided by square root 20, but you have variance now. So it's square root of 12.8 over 20. That is your standard deviation for x bar. So now you have a distribution like that. Mu is actually 5. You know mu is actually, this is the what is it called? That is my true distribution, right? With mu 5. So I want to looking for some value greater than A. That gives me 5%. That's what I'm looking for, right? So I'll use inverse normal. 0. Mu is 5. Standard deviation is square root of standard deviation of 12.8 divided by 20. That's all under square root. Okay, that's 6.316. Yeah, 6316. So using inverse normal, okay, probability x bar greater equals to A, as a less than A equals to 0.95, which A equals to 6.316. Okay, that is A. So that's A. Okay, for BI, a researcher decides to reject the null hypothesis if we observe the value is greater than A. Okay, when we observe something greater than A, we say, well, it's 5% only. It's not that easy to get. We'll reject it. What type of error is this called? Can we get something our distribution that greater than A when the mu is true? Yes. It's not possible. It's impossible. It's possible to use the same distribution to get something greater than A while your null hypothesis is still true. But we decide to reject it because we say it's such a lower chance to get that. Most of the time we reject it correctly, right? It's a really lower chance. But what's the chance you get a value greater than A? 5%, right? You have 5% of the chance you shouldn't reject H0, but you reject it. That's called the type 1 error. So what is the probability of type 1 error? It's just 5%. That's the same as your significant level. That is the same as your significant level when your mu is actually true. Does that make sense? Okay, 2. Using the value of A you find in part 1, find the probability that X bar less than A. Okay, probably X bar is less than A. A is 6.3, 6 something. Okay, but giving you that your mu is actually 7. Your mu is actually 7. It's not 5. Okay, it's not 5, which means your hypothesis test is wrong. Okay, you should reject it. So your X bar is with a new distribution, which is 7. What's that? Normally distributed. Okay, when it is actually 7, what's the probability you have a value less than 6.316? Let's have a look. Menu 552. Negative infinity to, let's just cancel that. I will save this value. Control VAR B. Let's see. Menu 552. Negative infinity to B. Standard deviation is actually 7. Your mu is 7. It's all like it's not your original distribution. It's a new distribution now. You're looking for our new distribution. What is the probability that is less than that? Standard deviation is square root 12.8 divided by 20. So it's 0.196. Okay, the probability on this distribution, the value I can get less than A is 0.196. 3 is the probability determined in part 2, describing either a part 1 or a type 1 or type 2 error or neither explained. Okay, let's just rewrite that. Let's think about the decision. Should I reject it when I observe something less than A? According to this question. Should I reject it? If I observe a value less than A, should I reject it? No, because the question tells us we only reject it when that is greater than A. So do not reject H0. Okay, given mu is actually that, should we reject it? Well, is that H0 is correct? When your mu equals to 7, your H0 is correct or wrong? Your non-hypothesis test, is that correct or wrong? Let me know. Yes or no? Your mu is actually 7. Is that your hypothesis wrong or right? What is the hypothesis test? What is your hypothesis test? Can you go back to look at your hypothesis test? Is that correct? Like, no, that is my actual. Your mu is that, but that's your hypothesis, what you assume. Do you have a right hypothesis or wrong hypothesis? The non-hypothesis is not good. You should reject it, right? That means H0 is not correct. You never look at the H1, you only look at H0 because we all talk about this H0. We never talk about accept H1 or not accept H1. We all talk about H0. So that's the probability that we do not reject H0, but when H0 is actually wrong. What's that probability? Is that a type 1 error or type 2 error? 2. That's a type 2 error. So that is actually a type 2 error. Okay, this is called a type 2 error. So you have like a really larger chance to get a type 2 error, which is 19.6%. You will get a type 2 error. You make a bad decision. Like say you made a bad decision. That makes sense? Your mu is the true mu value. Like it's not your hypothesis anymore. It's like what your actual mu is. Like your actual mu is that. Then you have a chance of getting this wrong. When you miss that, you get another chance of type 1 error. So you have 5% of the type 1 error only, but you have a 19.6 of the type 2 error. Okay? Okay, look at example 10 then. Okay, example 10. The mass of boxes of lentils is normally distributed with mean mu and standard deviation 15 grams. Okay, is normally distributed with, I don't know, whatever is the mu and standard deviation 15. Random sample of 16. So x bar will be normally distributed with mu of 15 on square root 16. To use the test the hypothesis, H0 is mu equals to that, H1 is mu not equals to that. Okay, this is two-tailed test. Right, I'll give you an example of one-tailed test last time. This is a two-tailed test. Okay. Find A such that probability x minus mu absolute greater than a level is 0.05. Okay, greater than 0.05. So what I'm looking for is, well, you know your mu is actually that. So in part A, your x bar true distribution is that. And that. Okay, this is the true distribution. That's correct. Doesn't matter what your assumption is, that's correct. So what I'm looking for is, okay, I'll just draw the graph and let you know what you're looking for. That's this. And you want this greater than A. So the distance here is A and A. So that's a 375 plus A. Okay, this value. So you want this part. And that's a 375 minus A. You want that part. You want that two part gives you 5%. That two part gives you 5%. So it's 2.5% on each side, right? 2.5% on each side. So, well, I can put in a Z. The way this book tells us is go back to a Z, but I don't really want to go back to the Z. So what I'm going to do is 553. Go inverse. It's 0.975. Okay. 0.975. Okay, so I'm looking for on the left hand side of that. This is 0.975 because that's 2.5%. And then mu is 375. That's given, which is the true mu. And then 15/4 is the standard deviation. I have that value. We have that value. I will subtract that by 375. Do you know why I subtracted? U plus A. U plus A is 375 plus A, right? So what I have is the probability x bar less than 375 plus A equals to 0.975. I have 375 plus A equals to 382.35, and then A is the subtraction of that, that's 7.35. Okay, A is that. A is that. So what I will have, that's A, okay, that's A. So if I observe something is at least greater than A, I have a 5% of type 1 error, right? I reject it. I observe something which is differs from 375 by greater than 7.35. Then I say I can reject it, right? That's 5% significant level. So for example, I observe something 390, I will reject it because on that side is less than 5%. 390 is even further, so I will reject it. But there will be a 5% type 1 error where I shouldn't reject it. When I observe the value here and here, I shouldn't reject it. That's still on the correct distribution, but I have rejected because I think it's not that easy to get. So I have a 5% of type 1 error. The type 1 error is always the significant level you're looking for. Okay, it's always the significant level. And that's 5% significant level. So let's have a look at B. B says mu is actually 380, it's not 375. So your X bar is actually follow a normal distribution of 780 and 50 on 4. That's the actual distribution. And what you're looking for is the probability that X bar minus 735 less than or equals to 7.35. Okay, what do you X could take? What you X could take? Well, X bar minus that is less than that. What's the range for the X? How I can get rid of the absolute value? You can't do why? Because that's not minus mu. Your mu is actually 380. So let's have a think. Something minus, okay, 375 is here. That's 7, you plus, that's a 7.35. That's a 7.35. You can plus that, you can subtract that. All of those values is a distance compared to 7.35, less than 7.35, right? That's all of those values I label as red has a distance from 7.35, which is less than 7.35, right? Like I have a smaller distance. So that's what I'm looking for. So basically I'm looking for the probability. This value plus 7.375. That's 38. That's the 38.35. Less than X bar. Less than. What's the lower bound? The lower bound will be 375 minus that is 76.65. Okay, it's that one. I'm looking for the probability between that. Don't worry about square root, just extend it and have a think what's the meaning of it and give the actual value of that. X. Let's label that as A. Let's label that as B. Menu 553. Oh, sorry. 552. Lower bound is A. Upper bound is B. Mu is 380, that's the new mu, and the standard deviation is 15 divided by 4. 0.734. Okay. Let's have a look at that. Okay, have a think about how we do that. We can't change it to Z. So we'll consider about what's the actual meaning of X. The X minus 35, which means this number between 735 got the distance less than 7.35. That's all the values in between that. Okay. So part C asks us to comment on the previous probability. So that's a probability that x less than 735, which is less than of this A value, given that mu is actually 380. So same as that, that's the probability. Do we reject it according to this question? Like we observe a value that distance is less than A compared to the mu. Do you reject it? When do we reject? Look at A. When do we reject something? No. Compare just say A. Why in the first one ask me to find something is 5%? Well, what's the meaning of this question? X bar minus 375. Like, okay, you assume 375 is correct, and then you observe the value. That distance compared to what I assume is correct as the mean got a distance less than A. Okay, got the distance less than A. Okay, less than A. But we only reject it when it's greater than A. We will not reject it when it's less than A. Is that correct? Because we reject it because it's less than 5%. That's A is give you exactly 5%. That's the 375. And that's the A. That's the A. When you observe something greater than A, you will observe the value here and here. That's when you reject it. Right? That's less than 5%. And now the second one says x bar minus 735, which is less than A. Should I reject it? No, I shouldn't reject it because the value I get is the inside one, which is greater than 5%, those values. Right? I shouldn't reject. So this sentence tells us what? No, like about the hypothesis. What's your decision? What's your decision? I mean, what's your decision about H0 and H1? Do you reject it? Do you reject it? Just if you observe something, do not think about probability, just look at the thing as circle. When you observe X bar, that is less than a unit from 375, do you reject it? Do you reject H0? No. Okay, I just want to say no, I do not reject it. So this is the probability. Do not reject H0. I just want to say do not reject H0 because you observe something which is greater than 5%, like the p-value is greater than 5%, it's already outside, like inside the like 2 distance. Okay, your actual reject part is that part, and that part you should reject. But what you have is x bar minus that is less than A, which is all the values in between here. You do not reject it. But given mu is 380, is that correct for H0 or not? Your null hypothesis is right or wrong? It's not H0, okay? So H0 is incorrect. H0 is 375. It's obviously not 375, it's 380. So you do not reject H0. And at the same time, you know that H0 is incorrect. What's that probability? What type error? What type error? Type 2. So what's the probability calculate? It's the probability of a type 2 error. Okay, what you calculate is the probability of a type 2 error, which is you do not reject H0 when you should reject it. That's a type 2 error. Okay? So the type 2 error is 73%. It's really high. Okay? You always have a higher type 2 error. Always have a higher type 2 error. So type 1 error is about 5%. Type 2 error is 73%. Okay, you need to know. The question will not tell you, this is a type 2 error, this is type 1 error. You need to announce this by yourself. They won't tell you that straightforward. But like by the notation here, we should see that the decision is we do not reject it because it's less than A. We only reject it when it's greater than A. Okay, when it's greater than A, so we do not reject it. If we do not reject it, and also you know that it's not correct, then that's a type 2 error. So I'm calculating the probability of a type 2 error, and that's 73.4%. Alright, okay, that's